A universe born not from a blueprint, but from a cosmic coin flip. Not a grand design, but a probabilistic event that, against astronomical odds, spontaneously ignited everything. 13.8 billion years ago, our universe exploded into being, a fiery torrent of energy and matter. But what if its very existence, its fundamental constants, the precise laws that govern every interaction, from the dance of galaxies to the shimmer of a quark? What if all of it hinged on a single, infinitesimal quantum fluctuation? This isn't idle philosophical musing. This is the chilling whisper emerging from the intersection of quantum mechanics and cosmology, pushing us to confront the deepest riddle of existence. Why is there something rather than nothing? For decades, the Big Bang Theory has provided a robust framework for understanding the evolution of our cosmos, its initial fiery state. It describes a universe expanding, cooling, forming stars, galaxies, and eventually us. But it remains conspicuously silent on the moment of creation itself. What the Big Bang? What was before it? And where did the initial conditions, the energy, the space-time, the very potential for reality come from? Classical physics, the physics of Newton and Einstein, struggles at this precipice. It demands a cause for every effect, a prior state from which the next emerges. Yet, at the absolute beginning, such a prior state seems absent. This is where the mind-bending realm of quantum mechanics steps onto the cosmic stage, offering a radical, almost heretical possibility. Quantum mechanics, the physics of the very small, paints a picture of reality far stranger than our everyday intuition allows. At scales smaller than atoms, particles don't have definite positions or momenta until they are measured. They exist as probability waves, a superposition of all possible states. This inherent fuzziness, this fundamental uncertainty, isn't a flaw in our instruments. It's the bedrock of reality itself, encapsulated in Heisenberg's uncertainty principle. It states that you cannot simultaneously know with perfect precision both the position and momentum of a particle, or, crucially for our cosmic inquiry, the energy of a system and the precise moment it possesses that energy. This principle allows for a breathtaking phenomenon, quantum vacuum fluctuations. The vacuum of space, far from being empty, is a seething, effervescent ocean of potential. It's not a void, but a plenum where virtual particles and antiparticles constantly pop into existence, briefly borrow energy from the vacuum, and then annihilate back into nothingness, all within the strictures of the uncertainty principle. It states that you cannot simultaneously know with perfect precision both the position and momentum of a particle, or, crucially for our cosmic inquiry, the energy of a system and the precise moment it possesses that energy. This principle allows for a breathtaking phenomenon, quantum vacuum fluctuations. The vacuum of space, far from being empty, is a seething, effervescent ocean of potential. It's not a void, but a plenum where virtual particles and antiparticles constantly pop into existence, briefly borrow energy from the vacuum, and then annihilate back into nothingness, all within the strictures of the uncertainty principle. These fleeting manifestations are not mere theoretical constructs. They are experimentally verified, underpinning phenomena like the Casimir effect, where two uncharged parallel plates in a vacuum experience an attractive force due to variations in these quantum fluctuations. Now, extend this concept to the ultimate vacuum, the pre-Big Bang cosmos. What if, before space-time as we know it, before matter or energy, there existed only a quantum vacuum, a state of minimal energy yet brimming with potential? In this primordial quantum foam, governed by probabilities, could a fluctuation of such immense magnitude spontaneously arise that it wasn't immediately reabsorbed? Could a tiny, unstable bubble of energy, a region of space-time smaller than a single proton, suddenly emerge, carrying within it the seeds of an entire universe? This is the audacious proposal of quantum cosmology, championed by pioneers like Stephen Hawking and Alexander Vilenkin. Their work suggests that the universe could have emerged from nothing in the sense of a classical vacuum. Instead, it sprang from a quantum vacuum, a state rich with quantum potential, where the laws of quantum gravity might allow for such a spontaneous genesis. Vilenkin famously argued that the universe can spontaneously pop out of nothing as a result of quantum tunneling. Imagine it, a universe tunneling into existence, much like a quantum particle can tunnel through an energy barrier it classically shouldn't be able to overcome. This isn't magic, it's probability playing out on the grandest possible canvas. In this scenario, our universe wasn't necessarily to be. It was, instead, a favorable outcome in an unimaginably vast lottery. Current cosmological models suggest that before inflation, an epoch we'll delve into next, a region of space-time smaller than an atom contained all the potential of reality, governed by these inherent quantum probabilities. The implications are profound. If our universe is a quantum fluctuation that's successfully inflated, it challenges our deepest intuitions about causality and purpose. It suggests that the universe didn't have to be. It have been otherwise, or perhaps not at all. The fundamental constants that allow for stars, planets, and life, the strength of gravity, the charge of an electron, the mass of a proton, could have been different. And if they were even slightly off, the intricate cosmic ballet that led to our existence would never have unfolded. This isn't to say this theory is without its challenges, or that it's universally accepted. The very concept of nothing in this context is debated. Is a quantum vacuum truly nothing if it contains potential energy and obeys physical laws? And how do we test hypotheses about an era for which we have no direct observational data, an era preceding even the cosmic microwave background? These are the frontiers where theoretical physics strains against the limits of empirical verification. But the elegance of the idea is compelling. The universe as a spontaneous, probabilistic event. Our reality, with all its intricate complexity and breathtaking beauty, emerging from the quantum foam like a magnificent, improbable bubble. It makes us ask, if our universe was merely the favorable outcome of a cosmic coin flip where the alternative was nothing, then what mechanism took that infinitesimal quantum spark and blew it up into the colossal tapestry of stars and galaxies we inhabit today? And what if that cosmic coin flip wasn't just a one-off event, but something that could happen again and again, creating an infinite multitude of realities? Building on that initial, mind-bending quantum instability, that fleeting, improbable spark of existence, we now turn to the mechanism that took a universe smaller than an atom and stretched it into the vast, observable cosmos we inhabit. From that paradox of a quantum genesis emerges one of the most revolutionary concepts in modern cosmology, cosmic inflation. The Big Bang theory, while incredibly successful, faced several critical puzzles that it couldn't fully explain. First, the horizon problem. Why is the universe so incredibly uniform in temperature across vast distances? The cosmic microwave background, the faint afterglow of the Big Bang, shows that regions of the universe that were never in causal contact nonetheless have almost exactly the same temperature. How did they know to equalize their temperatures? It's like finding two strangers on opposite sides of the Earth who, despite never meeting, spontaneously decide to wear identical outfits. Second, the flatness problem. Why is the universe so remarkably flat? In cosmology, flat refers to the geometry of space-time. If the universe's density were even slightly off the critical value, it would have either collapsed back on itself long ago or expanded so rapidly that no structures would have formed. Yet, observations indicate that our universe is exquisitely balanced, appearing almost perfectly flat. This fine-tuning seemed too coincidental. Third, the magnetic monopole problem. Grand unified theories, which attempt to unify the fundamental forces, predict the existence of extremely heavy, stable particles called magnetic monopoles, remnants from the early hot universe. Yet, despite extensive searches, not a single magnetic monopole has ever been detected. Where did they all go? Enter cosmic inflation, first proposed by Alan Guth in 1979 and later refined by Andrei Linde, Paul Steinhardt, and others. Inflation posits that in the first tiny fraction of a second after the Big Bang, the universe underwent an astonishingly rapid exponential expansion. During this hyper-brief epoch, space-time itself stretched by a factor of at least 10 to 26, possibly far more. To put that into perspective, imagine an object the size of a proton suddenly expanding to become larger than the entire observable universe, in less time than it takes light to cross a single atom. What drove this incredible expansion? The theory suggests a hypothetical scalar field dubbed the inflaton field. Before inflation, this field was in a high-energy, unstable state. As it rolled down to a lower energy state, it released a tremendous amount of repulsive gravitational energy, effectively pushing space-time apart at an accelerating rate. This negative pressure caused the universe to inflate dramatically. When the inflaton field finally settled into its lowest energy state, its energy was converted into the hot, dense plasma that constituted the initial conditions for the standard Big Bang expansion we understand. This process is called reheating. Inflation elegantly resolves the Big Bang's puzzles. The horizon problem. Before inflation, the entire observable universe was a tiny, causally connected region, allowing temperatures to equalize. Inflation then stretched this uniform region across vast distances, making it appear that distant regions were never in contact. The flatness problem. Imagine blowing up a tiny, wrinkled balloon to an enormous size. The surface, though inherently curved, appears virtually flat on a local scale. Similarly, inflation smoothed out any initial curvature of space-time, making the universe appear flat. The monopole problem. Inflation diluted any pre-existing magnetic monopoles to such an extent that their density became astronomically low, explaining their absence. But inflation does more than solve problems, it makes testable predictions. Crucially, it predicts that the universe should contain tiny, almost imperceptible variations in density that served as the seeds for all the cosmic structures we see today. These seeds are precisely those microscopic quantum fluctuations we discussed in the previous block. During inflation, these quantum jitters in the inflaton field were stretched to macroscopic scales, imprinting themselves onto the fabric of spacetime as slight overdensities and underdensities. And this is where the evidence becomes compelling. Missions like NASA's WMAP and especially the European Space Agency's Planck satellite have meticulously mapped the cosmic microwave background with unprecedented precision. The Planck data reveals a near-perfect match with the predictions of inflation, a universe that is incredibly flat and homogeneous, but with precisely the right spectrum of tiny temperature anisotropies, those primordial ripples that inflation predicts. These ripples are the fossilized fingerprints of quantum fluctuations stretched across the entire sky. They are the initial conditions from which gravity could sculpt galaxies, galaxy clusters, and the vast cosmic web. This observational triumph makes inflation a cornerstone of modern cosmology. It explains the universe got its large-scale structure and its overall uniform appearance. But if inflation is driven by a quantum field, then its starting conditions, its very roll of the dice, could have been one of countless possibilities. This brings us to a mind-bending, almost inevitable consequence of inflationary theory, particularly a variant known as eternal inflation. If the inflaton field can fluctuate quantum mechanically, it might not settle down everywhere simultaneously. Instead, in some regions, it might persist in its high-energy state, leading to endless, ongoing inflation, while in other regions it reheats and forms a new bubble universe. Imagine a boiling pot of water where bubbles continuously form, expand, and detach from the surface. In the model of eternal inflation, our universe is just one such bubble, one localized region where inflation ended. But in the vast, eternally inflating background, countless other bubbles could be forming, each with its own unique set of physical laws, fundamental constants, and dimensions, determined by the specific quantum fluctuations that governed its birth and the local parameters of the inflaton field when it reheated. Does this mean our reality isn't unique, but merely one face of a cosmic die tossed into an infinite multiverse? This is perhaps the most profound implication of inflation, pushing us beyond the boundaries of our observable universe into a realm of speculative yet mathematically consistent possibilities. If our universe is just one outcome, one specific set of quantum dice rolls, then the question shifts from why is our universe tuned for life to, in an infinite ensemble of universes, one is bound to be. It's a concept that simultaneously humbles and expands our understanding of existence, suggesting that the cosmic coin flip we discussed earlier might not have been a one-time event, but an ongoing, infinite cascade of creation. The idea of the multiverse, while not directly observable, is a powerful theoretical consequence of a highly successful theory that is well supported by empirical data. It's a leap, certainly, from observation to extrapolation, but one grounded in the very quantum mechanics that underpins our understanding of reality at its most fundamental level. It leaves us with a truly staggering thought. If the universe we see is just one outcome of a cosmic dice roll, what other realities might be out there, perpetually forming, forever expanding, in an endless quantum-driven cosmic ocean?